Okay. So this tool is used, for instance, when computing, at least I know in the cases for astrophysics or astroparticle physics, for instance, it is used, currently used, for simulating the transport of neutrinos in supernovae, for instance. It's a Boltzmann-like equation of state, actually with general relativity, and okay, it's much more complicated that we are going to derive here. This is just an example. And indeed, this is used because at least, well, depending on the density and the temperature, neutrinos are not in thermodynamical equilibrium in general with respect to the other particles of the system, okay, because they are weakly interactive. And therefore, to describe, for instance, the propagation of neutrinos inside a medium, in general, it is useful to adopt the scheme based on Boltzmann transport because it allows automatically to take into account the fact that neutrinos are not in equilibrium with baryonic matter. Okay, this is, for instance, a possible application. But it is used also in cosmology, for what I know, for instance, for computing, especially in the early stages during nucleosynthesis, it is used to compute indeed the production of the first light nuclei. Let me think about other possible applications. Well, indeed, the Boltzmann transport equation is at the origin also, but this I don't think we will do it. Well, one can derive also hydrodynamic out of the Boltzmann transport equation, both in the ideal regime, so ideal hydrodynamics, and also beyond the ideal hydrodynamics, namely in the cases in which also viscosity plays a role. So, for instance, it is used also for studying the outcome of heavy nuclei collisions, in which indeed you have two big nuclei, and the system that you form at the beginning after the collision is completely out of equilibrium. One cannot imagine that the system, at least at the beginning, is, let's say, it's thermalized, and therefore, also in that case, one uses this equation. Okay, so that's why I think it's useful, at least for a couple of hours, to spend our time to see what this Boltzmann transport equation is, and then, of course, this is just a very, very basic introduction. I'm not an expert of Boltzmann transport, which is still a field of research, but I think it's useful to see what's going on in this part of statistical mechanics, which is kinetic theory. Okay, so the beginning was to well, to establish which are the conditions under which one can justify this approach, which is indeed a phenomenological approach. Well, one of the things is that we consider the gas to be dilute in the sense that the density of the gas times typical length scale of the microscopic processes. Now we'll come to this point in a moment. Is smaller than one, meaning that basically on average, the particles are far away from each other, and they do not feel effects when they are far away from quantum mechanics, basically. Well, indeed, the quantity that should be included is the thermal de Broglie wavelength that we will introduce later. But you can think about it's like the de Broglie wavelength, but instead of having the momentum, one has the thermal energy, which is kT, basically. Okay. So these are the approximations of the dilute gas, in which quantum mechanics, well, indeed, will have a role, but on a specific term that we will introduce in a moment. The other approximations are that particles interact via collisions. So when they are close to each other, let me use the word close to each other, when the range or the distance of two particles is of the order of the range of interaction, then you have collision. Okay. Which are the other? Okay, that's it basically. Okay, the equation is written in a space which is the mu space, which is the space of position r and momentum of the particle. Okay, so basically what we do, what Boltzmann did, actually not me, of course. Suppose that we have a space which has as axis the three numbers characterizing the position of a particle and the momentum, the three numbers for the momentum. And you imagine you have a cell here of certain dx and dx. So here I'm just plotting the x components. Of course, one can generalize it. And this is a point that I call R and P in this case. And one introduced this function, which is the Boltzmann distribution function, which is a function of R and a function of P, and in general is also a function of T. R, P, T is a Boltzmann distribution. And what does this distribution? It's a probability distribution, if you want, if it is properly normalized. Well, basically, it provides the number of particles that are the position r with an uncertainty of delta r, and momentum p with an uncertainty delta p at time t. Okay, so let me write it explicitly. What f does. It's a counting. So f of r, p, and t times the volume of this space, and infinitesimal volume of this space, dr dp, provides the number of particles which are located in a position that is r plus dr, because this is the distribution, okay? And a momentum with the center at p with an uncertainty delta p at a certain time t. Okay, so it's a way to count the number of particles. What to say? Well, of course, this can be normalized in the sense that if I do the integral of f over the whole mu space, I should get the total number of particles. Okay. So if I do this, and the integral of f r p t and c dr over the whole mu space. Now, of course, you see here that this is a constant. It's time independent, the number of particles. Okay, if we fix our system to be a Gaussian box, and here I have a quantity that in principle depends on time, and therefore there must be some mechanism by which actually the total number of particles is conserved, right? Well, indeed, this mechanism is microscopic in the sense for each cell, we can impose the conservation of the number of particles. I will come to this in a moment. Okay, just a few words about the way one can imagine these two infinitesimal quantities. Actually, they are not, strictly speaking, infinitesimal in the sense that they should have a size that is, let's say, large enough to contain a significant number of particles. Otherwise, if they are too small, they just contain a particle, and it's not useful anymore. And at the same time, they must be small in order to build up, let's say, continuous and well-behaved function. Okay, so but this is very typical of this kind of studies. Okay? So all the information of the system, well, so the distribution of position and momentum is somehow encoded in this function. Okay. Oh, okay. So let me come now to dove sta il coso? Eccola là. A first equation that one can write, which is the Boltzmann equation in the case in which there are no collisions. So the first derivation will be the following. No collisions between the particles. And we can imagine to have a force F acting on the particles that depends only on R, the position. This is an external field, for instance. So it could be a magnetic field, it could be a gravitational field, electric field, whatever. Okay. So the particles have kinetic energy, and they have also, in principle, potential energy, which is derived from this force, which acts on the particles and depends only on the position. Okay. Okay. So one thing that one can write that due to the conservation of particles, conservation of the number of particles, which must be fulfilled also locally, in the sense that I'm not having here any leakage of particles, so any mechanism which destroys or creates particles. So then what I can write is that the number of particles, the infinitesimal number of particles N, well, this was written before as F of R T and T times dr dp. Now I suppose that I look at my system, so this is at time t. If I look at my system, my cell in particular, at the time t plus delta t, well, in principle, I have f, which is a function of a certain quantity that I can call r prime, and p prime. I write it there, and then I will write here the explicit relation, where r prime is just basically r plus velocity, just a definition of velocity. Velocity is momentum divided by the mass of the particle, a times delta t. And similarly, p prime is p plus f delta t. Okay. So at the, let's say, time slightly larger, slightly different than t, delta t, my distribution will have a dependence on r prime, p prime, and t prime, where r prime is provided by this number, so r plus p divided by n delta t. Then I have p plus f delta t, And here I have t prime, which is t plus delta t. And in general, now this is some multiplied by a infinitesimal element of my new space that I will call dr prime dp prime. Dr prime dp prime. So what I'm doing basically is to follow the evolution of my particles that were at the beginning, they were in a cell centered at R and T, and having a certain indetermination, so delta R dp. And then I'm looking what happens after a time t plus delta t to this cell. In general, this cell will move with a certain velocity, and also the momentum will change. No? So this cell will move and have another position, which is r prime, the prime, the center, say, of this cell. And in principle, it should have also different volume. Okay. So if the volume of this is dr dp, the volume of this is dr prime dp prime. In principle, this volume will change. But basically what I'm assuming, which is reasonable, is that actually the number of particles, which is the n, okay, which is of course it's finite but it's small, is the same as before. Okay. So there is no leakage, there is no source of particles, there is no way to destroy particles, and so therefore the number of particles that were in the cell must be conserved as time evolves, and the only thing that could change is the position and in principle also the volume. Okay. Okay, so now, well, I will conclude in a moment that actually the volume at leading order is actually the same. And to do to get this conclusion, so let me write again this. So F R P and T dr dp is equal to F R plus P divided by M delta T, P plus F delta T, and T plus delta T, and then I have dr prime dt prime, which is the basic conservation of particles. Conservation of particles. Okay. So now to see which is the relation between this dr and dp prime, dp prime, and the whole dr dp, I should calculate a Jacobian, no? Let me take just the x components. Of R and P. So if I just take the x component, of course one can repeat the same argument for y and z. I get that x prime is equal to x plus px divided by n delta t. And similarly, px prime is px plus f x delta t. Okay. And now let's compute the Jacobian, which is the determinant of the x prime dx, the x prime dpx, dpx prime dx, dpx prime dpx. So I just compute the derivative and then I build up the Jacobian of this quantity, which is equal to the x prime, the x is 1, and of course also this other term, the diagonal, is again 1, And now we see that these two terms are actually, when I do the determinant, are subleading in the sense that the x prime d, dpx is delta t divided by n. And what do I have here? Here I have to compute the derivative of this with respect to x, which is derivative of fx with respect to x times delta t. Because the force depends on the position, I said before. Okay, so then this is basically 1, and I have a term which is second order delta t. Okay, so something like delta t squared that I neglect. So at leading order, I can assume that the volume, the infinitesimal volume actually is the same as due to the evolution of the system. Okay? We will see the same conclusion later on, not today, when we will talk about the new Hill equation for the evolution of the phase space. Okay, so basically what I'm saying now is that this volume actually does not change as due to the evolution of the Hamiltonian, if you want, evolution of the system. And so the distribution at leading order, so at leading order in delta t, one can assume therefore that FRT is equal to f of r plus p divided by m delta t and p plus f delta t, p plus delta t. Okay, which is translates, if I do a series expansion of this, translates it into an equation which is already the Boltzmann equation in the case of collisionless Boltzmann equation. That is basically, I can expand this to a series. Now this is f of rpt, which cancel with this. Then I have the gradient of f with respect to r times p divided scalar p divided by m, the gradient of f with respect to p scalar f, and the partial derivative of f with respect to time. So I'm just doing the series of these and stop at the first order. Okay. So partial derivative of f with respect to time plus here I have the gradient of f with respect to the position scalar p divided by m plus the gradient of f, this time with respect to the momentum scalar f. Equal to 0. Okay? So this is called the collisionless Boltzmann equation because we are not taking into account the collisions and can be also interpreted as a total derivative if you want of f, no? Because f is a function of r, p, and t, and this this way of writing this equation basically encodes the fact that df, the total derivative of f with respect to t is equal to 0, no? Because the sum of the partial derivative times the hidden dependence on time, which is in r and p. Okay. So at leading order, I can assume that well, this equation holds true, which is an equation basically providing the conservation of the number of particles. Let me say, if I have to say something more about this, No, I think that's the first point. Okay. Now, the thing is that I want to introduce at some point the interaction of particles. So here I'm just assuming that the only way so let's say that the kinetic energy of the particle can change is due to an external force. Okay, so now I will introduce in my system the possibility of having collisions. So now we introduce collisions. And okay, so this quantity here is basically a derivative of f, which is this distribution with respect to time, which multiplied by delta t provides the total variation of f as a function of time, no? When I change t by an amount delta t. Now, if I introduce the collision, in general, the distribution will change also in a specific point, also because of the collisions, in the sense that I can sit in a specific position R and P, and basically counts the number of particles that will enter in this cell as due to a collision, or the number of particles that actually exit the cell as due to the collision. Okay, so then in general, when I introduce the collision at a fixed point, I have to introduce also not only this contribution, which is basically is called advection. Basically, is due to the fact that the system in principle can move and can have an external force. But I have to introduce this microscopic ingredient, which formally is written as derivative of f with respect to time, and here I write come si chiama collision all. So I can basically introduce the collision formally, just saying that this is not zero, but it is equal to a source term. Okay. Then now we will see how to actually provide a way to compute this derivative of f with respect to t as due to the collision. Okay. So basically, the picture, as I said before, is the following. So here I have R and T, and what happens is that some particles can enter here as due to the collision. So suppose that I have two particles here interacting, and then as due to the collision, maybe one of them will go here, and the other one will go here. Okay, so this is the initial state, and this is the final state. Okay, so then I can have a new particle entering in this volume, so with this specific R and specific momentum. Or I can also have two particles here that interacts, and maybe one of them or two of them will actually exit the cell. No? So I can imagine that, let me do the plot here, is R and P. I can imagine that the collision of two particles here is such that one of the two maybe will exit the system. Okay? So this is initial and this is final. So in some sense, I have to, so in this respect, I have to introduce the possible channels that increase the number of particles inside the cell, and the channels that decrease the number of particles inside the cell. Okay? So formally, I can write df dt due to the collision as a difference of r bar minus r that I will define now the following. Which, of course, they have a dimension of number of particles divided by time, no? Because they have dimension of f divided by t, which is 1 over t. And which is the interpretation of these two terms. Okay, so this r bar, if multiplied by dr and dp, and since this is a rate, is multiplied also by delta t, basically it's a way to count the number of collisions occurring in a temporal time window of delta t, so between t and t plus delta t, the kind of collision in which one of the particles after the collision enters the volume dr dp. Okay? So the thing that I said before, so as due to the collision, I can have the sum of some collisions which are occurring in the cells close to this one, they can actually move to the cell center at R and P, and therefore increase the number of particles which are there. Of course, I'm not talking only about the position, but I'm talking also about the momentum. Okay, so I can also have let's say a certain process that occurs at the same position, but changes the momentum of the particle, and therefore can well, remove, or it can go to another cell. Okay. Okay. And well, similarly, this other term R, it has the same meaning in the sense that R times dr dp delta t counts the number of collisions between particles that before were outside of my cell, and as due to the collision, enter this one of them entering the cell. Okay. Sorry, this is the thing that I said before. Okay, of course, entering the cell. Here is the opposite, of course. Okay, so number of collision in which at least so one particle exits, here enters and exits. Okay, so basically R bar R minus R, it's a net number, okay, counting the balance between the particles that enter the cell and exit the cell as due to the collisions. Okay. Good. Okay, so at this level, there's nothing really. I mean, it's just formal at this level. Okay, so now let us introduce some more physics. So collisions occurs and the same, okay, occurs between particles, This is already kind of approximation, which is, of course, reasonable, but it's an approximation, of course. But what I can imagine is that the collisions will occur really, really locally at the position R. So basically, I'm not taking, it's just that I'm taking the range of my interaction to be zero, basically, okay? So collision occurs between particles located at the same value R. Okay, this is an approximation that is basically an approximation in which the range of the interaction is very small, okay? It's very small. What kind of collisions I'm considering? I'm considering two-body collisions. Okay, this is also an approximation that actually is reasonable if the gas is dilute. So it's unlikely that three particles, four particles do interact at the same location R. So we will consider just two body collisions. Actually, there are in the literature generalization of to three body and even more collisions, which in some context, I know, for instance, maybe ions could be also important. For instance, we're considering the collisions of gluons, the interaction of gluons, in QCD, which you can have a vertex also with three gluons. And I know of some studies that have introduced these three-body interactions also in transport. Okay, but we consider just two-body collisions. And we also consider collisions which are elastic. Okay, elastic collisions. This is also very important because I'm just considering one family of particles which are identical in the sense that they have the same mass. Therefore, we just consider elastic collision. I'm not taking into account any process in which I create new particles or I remove some particles, which can in principle also be included by adding some reaction terms into the transport equation, which of course will complicate our life, my life especially, too much. Okay, so let's just consider elastic interactions. So basically, what I have in a collision, of course, is the conservation of momentum, which is P interaction, so a particle having momentum P with a particle having momentum P2 provides two particles, which are the same particles, but this time with P1 and P2 prime, P1 prime, P2 prime, okay? And I imagine that this process occurs at fixed R, which is, you know, it's very reasonable. I'm not taking into account, so I'm taking the size, the size of the interaction going to zero. Okay. Now, to take into account the collisions, which are again, as I said before, two-body elastic collisions occurring at a certain point R, I need to introduce a two-body correlation function or distribution function that I will just call capital F, which is a function of R, and the two momenta, P and P2, and also time. This two-body distribution function, which can be thought as a correlation function, if you want, what does it? Well, it counts the number of pairs of particles sitting at the position R with momentum between P and P plus delta P, momentum of the second particle between P2 and delta P2 at a certain time T. Okay? So dm equal to, there's no vector here, of course, sorry, is f of R P, P2 and T, and this distribution is multiplied by dr dp dp2. That provides the number of pairs of particles located at position R plus dr, with the first particle, so let's say first particle with momentum P, P plus delta P, and the second particle with momentum P2 plus certain delta P2. Okay? When at the time t, of course, at time. So basically, this quantity is it's a quantity that it allows me to count the number of collisions occurring at a certain position R, and also to know the distribution of momentum of the initial momentum. Okay. So these are very important quantities, and actually I can write down an equation actually at the end, only if I can assume a specific property of this two-body correlation function. It is crucial in all this derivation of the Boltzmann transport equation. Okay, now, okay, this quantity here that I just remove, basically just counting of particles, okay? Now I will have to introduce, at least in a formal way, which is the microphysics of the process. And for the microphysics of the collision, since I'm talking about two-body interactions, two-body collisions, well, I must remember something of a couple of years ago of scattering theory, in which you have the differential cross-section I remind you that the cross-section sigma is the total number of reaction occurring, so the rate of reactions divided by a flux, okay, times 1 if I have just one particle in the target, okay. So dimensionally, the sigma to the cross-section is a rate of reactions or rate of collisions divided by a flux, which counts the number of particles interacting as a function of, in time and in surface, okay? So this flux here is number of particles divided by a surface and time. Okay, just to remind you, which are the meaning, which is the meaning of the cross section. And this total cross section, and here I'm writing a differential cross section, which depends on the solid angle, for instance, depends on the momenta of the particles. Okay, but anyway, from the Fermi golden rule, we have seen in the past that the differential cross-section must be something that contains, apart from some constant and apart from the relative velocity, the most important thing is that it contains something that is a matrix element which contains the Hamiltonian of the interaction that I call a TIF, where TIF squared is a matrix element providing the transition operator. Is a matrix element of the transition operator. So something that tells so here it's if I have a final state and an initial state, here I have, let's say, the interaction Hamiltonian. Okay, something like that. Or a potential, depends on the which scheme I'm adopting for perturbation theory. Okay, so basically, well, here there is the interaction of the particles, which I will not touch. I will just, let's say, introduce it as a matrix element squared. Okay. And the other thing, the other ingredients of the Fermi golden rule, of course, is the conservation of form momentum, which is conservation of energy times the conservation of momentum. So I have no space here, and then I just write conservation of energy and momentum. Okay, I will write it explicitly in a moment. And I have the phase space, the final phase space, which is dp1 prime and dp2 prime. Okay, so the cross section in general has the following structure. It has a matrix element that contains the interaction, okay, conservation of energy and momentum, and the phase space of the final state, which is now dp1 prime, dp2 prime for two-body collisions. Okay, and in principle here, but not in principle, here there is an initial state which depends on the momentum of particle 1, which I call P, and the momentum of particle 2, which I call P2. Okay? And somehow I have to integrate, I will do it in a moment, I have to integrate over the final phase space and the initial phase space on the, for what concerns the momentum of the particle 2. Okay? So basically what I can write here, once I introduce the two-body correlation function and to some extent a cross-section, which I will just consider this structure here, I can correlate these quantities exactly with the quantity with the rates R and R bar that I was introducing before, which are now expressed in terms of the microphysics of the interaction. So let me write in this way that now R dp, sorry, dr dp, and there was a delta t. Now what I'm saying is that this quantity here which was indeed the total number of particles that are going out of my cell as due to the interaction. Now this quantity here, I write it down and then I will comment on this. This integral dp2 dp1 prime dp2 prime. Then I have the matrix element squared, here squared. Then I have the conservation of energy and momentum, which is a delta 3 p plus p2 minus p1 prime minus p2 prime times the delta of energy conservation okay. There's no space, so these are times continues there. And crucial ingredient is this two-body correlation function, which was this capital F, which is a function of R, P2, R, P, P2, and time. Okay? And this, of course, this quantity is multiplied by this phase space delta T, so times dr dp delta T. Sorry, but with one blackboard it's difficult. But okay, so this quantity here, as I said before, counts the number of particles which are going out of my cell. The cell is sent as this volume, and this is a rate, so it's the number of particles divided by time, but then multiplied by delta t. Okay, and I will recover this here. So basically, what I'm saying is that the rate is provided by this expression here, in which, as you see, the structure is basically the structure of a cross section, or if you want, of a rate of reaction, better to say, in which I have the matrix element, the conservation of momentum and energy, the correlation function, two-body correlation function, which somehow is counting the number of particles that do take part in the collision, and then I'm integrating over the final phase space and the momentum of particle 2, okay, in order to get what happens at the cell, which was centered at R and P. Okay, so this is more or less the idea. Now, of course, so I have to say something more about that. Questo lo dico adesso, lo dico dopo, lo dico adesso, o lo dico dopo, no, lo dico adesso. Now, one thing that one could maybe remember from scattering theory is that if I have, let's say, not particularly weird Hamiltonians, in general, I can assume that they have the feature parity conservation and time reversal. Okay, so in the sense that if I flip the sign of momentum, that will not change my cross section. Or if I do a time reversal, which means that I flip the sign of the momentum, and at the same time I'm changing what is initial and what is final in my matrix element, then typically these two operations provides the same result for the matrix element. So in other terms, I'm writing here. So TIF, which was something like this. It's an Hamiltonian of interaction in an initial state. And I'm saying that if I do inversion with I and F, I will get the same. Okay. Okay, now here I have to be more maybe more correct. So here there would be, instead of root, let's say this bag term, which is Hamiltonian interaction. Actually, it should be the operator of T that we introduced last year, which is this transition operator. Okay, but okay, just to I will not use it in any case. So just to stress that here there is the interaction, and typically these matrix elements, they are invariant with respect to exchange of initial and final state. So let me write in a better way. So if I have P1 and P2 as a final state, P1 and P2 prime, and here I have the transition operator, T, which enters directly in the cross section, and this is P and P2, and I have the square modulus of these. Now one can show, and we have done last year, I think, but for the ones who are not familiar with this, I can comment. This is equal to T and P modulus. This equation is called detailed balance. Okay, and it can be obtained by assuming that the interaction is not is very invariant and time reverse invariant. But I mean, intuitively, it's very reasonable in the sense that I'm saying that the probability to go from the initial state to the final state is the same as going from the final state to the initial state, just because we know that at the microscopic level, at least, the physics is, let's say, time invariant, unless I consider in some processes which are, of course, not even imagined at the time of Boltzmann, which are the CP violating processes. Okay, but in classical, let's say, not touching these subtle violations of conservation, in most of the cases, I can assume that I have time reversal in my Hamiltonian and also parity, time parity symmetry with respect to parity. And then this basically translates into an invariance of this matrix element if I exchange the initial state and the final state. Of course, the microphysics is the same in terms of matrix element. What is the difference if I have a system out of equilibrium is obtained when I actually multiply this quantity by the times the phase space. So if I have the phase space of the final state is somehow larger than the phase space of the initial state, even if the matrix element is the same, then I can have that the rate of reaction prefers a direction instead of the other one. Okay, so this is important, and indeed it will come in a moment. Okay, so the microphysics here is invariant with respect to exchange of initial and final state, but this is not true when I consider the structure that I have here in general. Because here I have, okay, I have conservation of energy, but I also have this quantity here. And indeed, this has no time reversal anymore. So let's say the global quantity has no time reversal anymore. And indeed, we will show, but probably not today, but next time, that a theorem holds true, which is called H theorem, which provides, let's say, a possible explanation of the let's say, if you want, the second principle of thermodynamics. Okay, so so this was R. So now similarly, I can write a similar expression also for R bar, and I will write directly the integral since the interpretation is the same as before. So again, I have to integrate over the momenta of the final state and the initial state. Then I have, okay, I have in principle, I should introduce t at 5, but as I said before, this equal as cannot. Okay, let's do it properly. So, facciamo così, F3 squared, and then I will introduce this later. Then I have, okay, the conservation. I will not write the argument, which is the same as before. And here I have the two-body correlation function, which is again a function of R. Now I have P1 prime and P2 prime, and then P. Okay. Okay, so let's notice one thing, that here you have the conservation of energy and momentum, and then I have to integrate of this conservation. Well, this provides basically a constraint between the energy of the particles and the momentum, P, P2, P1 prime plus P2 prime. So actually, this quantity here that I'm integrating over actually depends on in a subtle way from the momenta of the particle P and P2, because they are not uncorrelated. This P1 prime, P2 prime actually depend from this conservation of energy and momentum. They depend in general also from P and P2. And I'm integrating over P2, P1 prime, P2 prime, okay? And also here there is a dependence, of course, on P1, P2, P and P2, okay? So now let me do okay. So here this process, so this function here, what does this function? This counts down the number of particles which are located in R with momenta between P1 prime, P2 prime, and uncertainty, and which provides a particle as a final state with the momentum which falls inside the cell. Okay? So let me maybe write a bit more explicitly. But the interpretation of this R bar was that at the microscopic level is that I have, let's say, two particles, so P1 prime, P2 prime, that at some point collide and provides P and P2 with P inside the cell, the volume of the cell, dr dt. Okay. This was the interpretation of this term, of this contribution to the collision term. Okay. And now I wrote before that my collision df dt collision was equal to the net number of reaction rates, which is this R bar minus R. And here I will now assume explicitly that I will have this invariance. And therefore, I can write this difference just as the following integral. So here I have dp2, dp1 prime, dp2 prime, matrix element. Then I have the conservation delta 4, which I will not write explicitly. And now I have to be careful here. So here you have then f of r, p1 prime, p2 prime, t, minus the same quantity, but this time contains p, p2, and t. Okay. And of course, now this r bar r minus r, for what I wrote before, is basically equal to the derivative with respect to time of f as due to the collision. So this is the expression of the the Boltzmann equation, the full Boltzmann equation will be the following: gradient of r scala, gradient f scala p divided by m plus the gradient of with respect to p of f scala f is equal to what this quantity here, okay? R bar minus r. Which of course looks very, very nasty, and indeed it is nasty. And even if I have to actually do an approximation, here is even more nasty, in the sense that, as you can see here, there is on the left-hand side, there is a quantity which I want to find out what it is f, as the distribution function. And on the right-hand side, actually, I have another function, which is f, it's capital F, which is a two-body correlation function. So actually, in this, written in this way, basically, I have no way to solve, to close my system, my equation, because I don't know what f is actually, okay? And indeed, this equation written in this way, it's just one equation of an infinite hierarchy of equations that we are not going to study, which are called DBLK hierarchy equation. Okay? I don't remember all the name of the authors. And so at some point I have to do a further approximation to close my system, in the sense that in this way I don't know what to do out of this actually. Okay? Because I have two body correlation function here, and here I have one body correlation function. Now, and here comes the main assumption of this derivation of the Boltzmann equation, which is the assumption of molecular chaos. Molecular chaos. Il caos si scrive con l'H, sì, penso di sì. Si scrive con l'H caos, sì.
Sì, sì.
Giusto, ok, grazie. Voi potete googlarlo subito. Okay, what is this assumption of molecular chaos? Well, basically, the assumption is the following, that the two-body correlation function for instance, let's take the second one, but it's the same for the first one. So f of r, p, p2, and t is just the product of the two one-body correlation functions. times f of r p2 t. Okay. So what is saying this equation is that the distribution, well, apart from space, which is the same, but the distribution, the probability, let's say, to find a pair of particles with momentum p and p2 is actually the product of the probability of finding a single particle with p and another particle with p2. Okay, so basically, I'm just saying that there's no correlation. So the joint probability is actually the product of the two probabilities of the single distribution. Okay, okay. Let me say if I have another way to say. Okay. Okay. So in principle, so therefore I'm neglecting the correlation of P. Okay. So it's like that having a momentum P and P2 for the pair of particles does not depend on anything but on the single probability of having P and P2. Okay? Now this relation is actually crucial for all the discussion of reversibility because it's a strong assumption of somehow that is telling me that the microphysics of the process, well, the fact that I have so many collisions actually destroys the correlation of particles, and the fact that I have this destruction of correlation actually will end up with the irreversibility of my process. Okay, so if I keep, actually, one can show that if I keep f as it is here, but we cannot do in this scheme, one has to introduce another scheme. Actually, at this level, the equation of Boltzmann is still a time invariant with respect to time reversal. And actually, it's this specific hypothesis which actually introduce the irreversibility, which at the end is due to the fact that the correlation, microscopic correlation, are smeared out as due to the great number of correlations, of collisions, of course, first of all, and so mainly the total number of particles. That's one thing. And the other thing is the typical time scales that during which I'm looking at my system. So we are coarse graining not only in momentum and space, but we are also coarse graining in time, in the sense that typically we are not interested in what's going on time scale of, I don't know, 10 to the minus 10 seconds, so on a microscopic time scales. We are mostly interested in time scale which are, let's say, macroscopic time scales, and therefore, at such temporal scales, all the possible correlations are actually smeared out by the fact that I have so many collisions, so many particles that actually these correlations so drop basically exponentially. Okay. So this is an assumption, of course, but it's a strong assumption that actually is at the heart of the argument explaining the reversibility of Boltzmann. Okay, the molecular chaos assumption. One can, among the books that I was suggesting you at the beginning, some of them they discuss this assumption a lot, because basically these all the say the debate over the Boltzmann equation basically is due to this assumption. Okay. Now let's follow this assumption, and therefore my equation now looks a little bit better. So the derivative of x with respect to time, then I have the gradient scalar P divided by n plus gradient P of F scalar F. This is the left-hand side, the Boltzmann equation, and these are integral over dp2, dp1 prime, dp2 prime. Then I have, okay, the TFE for modulus, and okay, the conservation that I will not write explicitly times. Okay, so let me write it here because there's no space there. So I have f of r p1 prime t times f of r p2 prime t minus f of r p t and f of r p2 t. Okay, so and that's it. So that's the Boltzmann equation. Under the, in presence of collisions and under the hypothesis of molecular chaos. The hypothesis of molecular chaos allows me to write the difference between these two capital F as just as a product of these two one body distribution function. Okay. Now, as you can see now here, I have here that the variables P2, P1 prime, P2 prime I'm integrated over these quantities. The only momentum of which I'm not integrating is P, which is in here. And of course, there is a dependence on the R of all this expression and also on time. Okay. And the function f, which is the what I want to find out, it appears here with derivatives, which I do the derivatives with respect to time and position and momentum, and here enters in integration. So this equation technically is an integral differential equation. Not because the f appears with derivatives here, and I'm integrating over there. Okay. So as you can imagine, it's very complicated to solve this equation, but I mean, people are really doing this numerically with very complicated codes, of course, for solving this equation in different contexts of physics, as I said. Okay. So the goal, of course, of solving this equation is to find the final distribution. Okay. So there is another way to write this quantity. Of course, at some point, well, this is not very important, but we will use the Boltzmann equation in this form. But in principle, there are some integrals that can be done easily, in the sense, well, formally, I can integrate over dp1, for instance, and I can drop the delta 3 of conservation of momentum. There's a line here. Okay, so I can do the first integral in dp1 by using the delta 3. So then I will have an integral of dp2 and dp2 prime and something. Just to comment on the fact that this integral is very nasty, but actually there is a delta here that allows me to reduce this integral. But actually, well, it will establish also some complicated correlations between the variables now inside my matrix element, of course. Okay. And then I have here a conservation of energy, which is E plus E1 minus E1 prime minus E2 prime, and all the other terms, of course. And then I can also do these integrals. So I write this as dp2 and d sigma. Well, actually, I can be more explicitly. So this would be P2 prime square modulus dP2 prime, and then I have a solid angle, writing this in spherical coordinates, and I can use the delta function of conservation of energy to get rid of this integral of dP2 prime. Okay. Okay, so at the end, we'll end up, so actually, it's not a six-dimensional, well, nine-dimensional integrals, but actually, it's a five-dimensional integral, okay? So if I do this integration, actually, we'll have an integral over dp2, and then the solid angle of p2 prime, okay? Of a quantity that now has a matrix element and a distribution function, and there will be also a p squared, p2 squared, which is a function of all these other functions, all these languages. Okay, so this is just comment on the fact that at some point some of these integrals can be done. Okay. Now, let me see what I need to say. Well, of course, now at some point one can also introduce the cross section, but since I will not use it in this version of the cross section, I will not do it. Okay. So here one can introduce the cross section, which was actually proportional to the matrix element and to the phase space. So people normally, when doing numerical calculations, introduce in the collision integral the cross section of the microphysics processes. Okay, so this equation is of course very complicated, and actually we will not even try to solve it because it's impossible to do it analytically. What we will do is to find, first of all, which is the, well, we can infer what is the, let's say, the functional form of the distribution at equilibrium, first of all. So we will do this maybe today, still have time. And next time we will explain the H theorem, which is, let's say, the Boltzmann way to explain irreversibility of macroscopic systems. Okay. So the first thing is to find, at least let me do this today, which is the distribution of equilibrium. Okay, when I have equilibrium, when I will reach at some point equilibrium, my function, my distribution function f of r, p, and t will end up being a function that I call f0 of r and p. There's no time dependence anymore. Okay? So no explicit time dependence. Because in a stationary condition, I can imagine that the derivative of f with respect to time, the partial derivative, is zero in stationary condition. Okay. In general, it will depend on r and p, so it's a function of the position and of the momentum. But a stationary condition, which are the conditions which are realized in thermodynamic equilibrium, which is our definition of thermodynamic equilibrium, I can imagine that this function does not depend on time anymore. So let me do the following two assumptions. Assume 1 and 2. The first assumption that I do is that f does not depend on r. So I have a uniform system of uniform density, if you want, uniform particle density. And let me assume also that F, so the external field, is equal to 0. In this specific approximation, I can provide which is the functional form of F0 as predicted, if you want, by the Boltzmann equation. Okay? In general, this is more complicated, and we have not developed the technology to do that. But at least in this case, we can do it. We can find an argument that will, that at the end, will provide me the form of F0, the equilibrium, which will turn out to be the Maxwell-Boltzmann distribution of velocity. Okay. So, so under these conditions, the Boltzmann equation is basically this, no? It's df dt, where f is a function of p and time. Now this is equal to df dt collision. And since at the equilibrium this must be equal to 0, for what I said before, then df dt collisions is equal to 0 at equilibrium. Okay? So when the system is stationary. And what that means is that since the integral has the integram has a quantity which is the matrix element, which is positive, definitely positive, and I had okay, so in df dt collisions, it was an integral of tp2 dp1 prime dp2 prime. Then I have the matrix element squared, then I have the delta, blah, blah. And here I have, let me write in the following way, and I will explain you what are these quantities. Okay, let me write this in this way, f2 prime, f1 prime minus f times f2, where f is just f of r, p, and t. This is in general, in general. Now, in this specific case, I'm doing here now does not depend on r, but this is just a way to write the Boltzmann equation in general, in a more compact way. So this f is just this function here. F2 is the same function with p2 and t. F1 prime is f of r p1 prime dt, and similarly f2. Okay, So I'm just indicating here with f the function of r, p, and t, which is my the goal of my equation, the solution of my equation. F2 is a function of r, p2, and t. F1 is a function of r, p1 prime, and t, and similar. Okay, it's just a notation. Okay, so now if the collision term pf dt called equal to 0 implies that this term is equal to 0 at equilibrium. So basically, I have to impose at equilibrium that the function, which is now f02 prime, f02 prime times f01 prime must be equal to f0 times f02. Okay? Which written in a more explicit way, coming back to the notation that we had before, f0 to prime is actually f of p2 prime, f0. I'm not writing t because it does not depend on t at equilibrium. 0 means equilibrium. Then I have fp1 prime is equal to f0 of p and f0 of p2. Okay? So this condition that holds true at equilibrium means that the distribution function at equilibrium must obey this equation. Okay? So let me take the log of this, the logarithm, and if I take the logarithm, I get that the logarithm of f0 p2 prime plus the logarithm of f0 p1 prime is equal to the logarithm of f0 of p plus the logarithm of f0 of p2. Okay? Now, as you can see, this is one scalar equation. First thing that one can observe is a scalar equation. And what is written here is, let's say, after the collision. So it's expressing the fact that after the collision, or before, it depends on what I define as before and after. But anyway, P and P2 were at the stage of the collision, which is before, for instance, the collision. P2 prime, P1 prime is after the collision, or it could be the opposite, but in any case, what happens is that after the collision and is equal to before the collision, this quantity, so this log of f0 is conserved. Okay. For each of the two momenta. Now, what you can think about a quantity that a scalar quantity conserved in the collision. This elastic scattering for this energy. Okay. One can do it more general, but of course this is very reasonable. So here I'm saying that there is a scalar quantity associated with the momentum of the two prime, momentum 1 prime, momentum p, momentum 2, which is conserved due to the collision, so after the collision, if you want, and therefore I can think about conservation of energy. Now, what is energy here is just p squared, right? So kinetic energy. And therefore, I can assume that F0, well, the log of F0 must scale somehow with p squared in such a way that no, p2 prime squared plus p1 prime squared is equal to p squared plus p2 squared, which is basically the conservation of energy. Okay? And now if I assume this scaling of the logarithm of f0 with p, then I can basically write that f0 of p must have a form must have a shape like this. C e to the minus p squared a, where I have indicated with p squared the square modulus of p. Okay, where c is a normalization constant that I will derive not today but next time, and a is a constant also, and I put a minus here in order that a is positive, just because of the possibility to integrate over p, in the sense that I know that the momentum, the modulus of the momentum has no upper limit. Therefore, since this quantity, when integrated, must give me a number of particles, I have to be sure that the integral converges. Okay. So then I have introduced a minus here, and I consider A to be a positive quantity just because in this way I can integrate over P. Okay. Now, maybe it's not very clear written in this way, but basically this exponential dependence on the square modulus of P is basically the Maxwell-Boltzmann distribution for the velocity of particles. Okay? Maxwell-Boltzmann distribution for the velocity of momentum, if you want, of particles. La Maxwell-Boltzmann l'avete fatta da qualche parte? Della distribuzione delle velocità? Sì? Ok, comunque noi la riprenderemo la prossima volta. Magari se l'avete già vista, quindi posso pure andare un po' più veloce la prossima volta. But maybe let me just make some more comments. So here I have used the conservation so I found that this quantity must be conserved before and after the collision, and I found an example, which is the energy, that is indeed conserved. In principle, here I can have a more complicated dependence. I could also have a function f0 which has this form p this would also be fine. So structure like this that depends on the square modulus of P, then it has a normalization, and that is a linear dependence on P, no? Okay, there's a P scalar P0, okay? So a function like this would also work fine with the conservation that we wrote before, because indeed I have not only conservation of energy, but I also have the conservation of momentum, and so this would also be fine, okay? Here I'm writing a specific case in which P0, which can be interpreted as a kind of average momentum, is equal to 0, okay? But a structure like this could also work. The reason for which I'm neglecting this possibility is just because I have a scheme here in which I have said that F, which is the external field, is equal to 0. So then I do not expect to have let's say a momentum with an average which is different from 0. Okay, since I do not have as a vector. Okay, since I do not have any, let's say, external force expected on average, the total momentum of the system will be 0. Okay, and also the average moment as a vector. Okay, but these also would be fine. Okay, cos'altro vi dovevo dire? Okay, so well, another comment that I can do is the following. So this is the distribution of the system in a stationary state, which is our thermodynamical equilibrium, and it has the Maxwell-Boltzmann shape, typical distribution of velocity of momentum. And you might remember that this specific distributions is associated with the ideal gas, in which, and in the case of the ideal gas, we will see this afterwards, basically there's no interaction between particles. So the equation of state of ideal gas is basically obtained by assuming that the only term of the Hamiltonian is just the kinetic term, but for a confining potential, which is basically, it's just basically the walls of the box that contains my gas. Okay, but the particles are not interacting with each other. Now, the thing is that if you really assume that particles are not interacting with each other, strictly speaking, and this is basically well, one let's say conclusion out of the Boltzmann equation, you will never reach equilibrium. If there is no interaction, there is no thermodynamical equilibrium. You can just have particles which are free streaming, each one with its own velocity, and doesn't talk with the other particles. Okay. And now, so the thing is that actually ideal gas is, of course, an approximation. And the lesson one can learn from the Boltzmann transport equation is also the following, that to some extent, I need some microscopic interaction in order to have equilibrium, okay? Even if this kind of interaction is, let's say, negligible, or it's very small for what concerns the equation of state, does not provide a significant contribution to the equation of state, such as the case of the ideal gas. In any case, the interaction, even if they are very weak, it's necessary in order to get a thermodynamical equilibrium, to get a distribution like this, which is indeed the distribution of equilibrium. Okay, so these are very important points. At some point, so we need the interaction, even if it's very weak, but to reach thermodynamical equilibrium, we need an interaction. Then, at the end of the day, my equation of state can be independent from this interaction. It's very weak, as in the case of the ideal gas, but in general, from the conceptual point of view, in order to talk about thermodynamical equilibrium, I need microscopic interactions. Okay? So adesso è l'una, and direi che ci fermiamo qui. E la prossima volta, allora già che vi chiedo, quindi la Boltzmann distribution delle velocità l'avete vista, quindi magari ci andrò, non vado molto veloce su questa cosa. L'altra cosa che volevo sapere, che sempre ha a che fare con la stessa, poi di fatto, è se voi di Kinetic Theory avete fatto il solito problemino, quello immagino di sì, però quel calcolino simpatico, dove faccio un disegnino per lo capire subito. Il disegnino che si fa in Kinetic Theory, appunto di solito anche al primo anno si fa, in cui si vanno a prendere le particelle che vanno a scatenare con una parete, tornano indietro, e c'è una variazione di impulso. E questo, diciamo, permette di calcolare la pressione. Quello l'avete fatto quel conticino, vero? Ok, quindi sì, in fisica 1 di solito si fa, cioè, diciamo, di calcolare la pressione in modo microscopico a partire dall'impulso scambiato tra la particella e la parete del contenitore. Quindi anche su questo la prossima volta posso andare, diciamo che posso andare molto veloce, vi ricordo più o meno come funzionava. Semplicemente mi serve ricordarvelo per andare a calcolare queste normalizzazioni, questi fattori, però quindi posso andare comunque abbastanza rapido su questo. Va bene, allora ci vediamo giovedì. Opla.
Arrivederci, buon pranzo.
Arrivederci.
Arrivederci.